All right, so today's lecture, and actually this is the first of two lectures, well, three lectures really, on machine learning. The first two are going to be on the more algorithmic side of machine learning, and the third one will be on the more theoretical side of machine learning. And these will not yet cover deep learning, which is a subset of machine learning, but one that we're going to cover in much more depth because it is sort of one of these emerging core topics or already emerged core topics in AI these days. But these lectures, these ones will set the groundwork for a lot of our later discussion of other algorithms in machine learning, as well as some of the other sort of more advanced techniques. Before I start though, so this lecture is going to go through the following. We're going to talk a little bit, very briefly, about what machine learning is. I presume actually most people here will probably already have been exposed to some machine learning. It's so ubiquitous these days that you almost can't. If you're taking a graduate AI course, chances are you've already seen some machine learning. It wasn't always like this, by the way. It used to be that AI courses had to include an introduction to machine learning from the very, very basics. And this is still going to be an introduction because we want it to be kind of self-contained. But it certainly maybe will go through a little faster than you might be used to in other AI courses if you've seen that. We're going to talk about what machine learning is. Then we're going to cover two main topics here, linear regression and linear classification. And even though these are both very simple areas, they do sort of underlie a lot of more advanced algorithms in machine learning. So it's very important to understand how these things work in order to understand kind of what we can do, how we can build on top of them. Before I start though, are there any questions kind of about logistic things? I know we've moved the midterm. We've also have a homework out now. Are there any questions that are sort of coming up that we haven't answered on Piazza yet? Yeah. Sorry, what was that? There's only going to be one midterm test, correct. Instead of a final, we're having the final project, so there's no final exam. Yeah. So you only will be tested on maybe 2/5 of the material. Though homework's on the rest, so you'll still have to learn it. All right, so let's talk about what machine learning is. And I'd like to give this example about machine learning because it's one that's both everyone's sort of very intuitive and it's what you're going to do on some of the homework problems. And this is this sort of classic problem now, which is at this point become almost cliche in machine learning. But it's this task of digit classification. So the idea here is you are given, in this case, 28 by 28 pixel images of a digit. So a digit 0 through 9. And you want to write a program which is going to say, given this image, what digit is that, right? So you want to basically write a program that takes as input one of those things. This is again from what's called the MNIST dataset, sort of a very famous dataset in machine learning. People still use it as like an initial toy dataset now, but it used to be actually considered very big as datasets went. You're given one of these images, and you're tasked with writing a program that'll output what digit that is. And so there are a couple ways you could do this. So I think the classical kind of programming paradigm for this is that you would sort of think to yourself, what makes a 5 a 5? And I'd write these little image processing routines that would look for characters of a 5. Maybe there's like a straight part and a perpendicular part on top and then a rounded part in the bottom. Something like that. Of course, they're not quite perpendicular there, so you have to have some tolerance on that. Maybe you fit lines to it and fit curves to it and have some model about what makes it a 5 versus something else. Similar with an 8 with all the digits, right? And this is what people did for a long time. This is how kind of computer vision started with things like digit classification or face recognition. People essentially would write these sort of models about what they thought a face or a digit should look like, and they tried to apply that to this code or to this data. And what people found was this is actually incredibly hard. So we sort of take it for granted because we're so good at this as humans, but this is actually very, very hard for a computer to do, right? So when a computer sees that, it doesn't see the patterns and the high-level object that we see. It just sees a bunch of pixels. And how you go from that to a classification of digits being invariant to moving it around a little bit and scaling a little bit or rotating or the different types of ways people write 5s is very, very hard. And it was very hard to come up with robust methodologies that could do very well on these things. The alternative approach, which is really the machine learning approach, is that you don't bother trying to do that. Instead, what you do is you create a data set with a bunch of images and their corresponding label, right? Their digit that they are between 0 and 9. And you kind of let, to sort of, for lack of a better terminology here, you kind of let the program write itself. You let the computer write its own program to figure out how those things map from the images to the number 5, say. Now, of course, that program we mean there is actually ends up being a very simple one structurally. There isn't a lot of sort of logic in that program. It's mainly just linear algebra. But it is kind of a program, and it has some parameters of this program which you tune to make it perform the tasks that you want it to perform. Now, technically, this is actually what's called the supervised learning approach to machine learning, which is a subset of all machine learning, but it's the one we're going to mainly focus on here. We're going to mention unsupervised learning a little bit, and when we talk about probabilistic modeling, we'll actually cover their things in unsupervised learning. But here we're really going to be focusing on supervised learning in that paradigm. So this is the paradigm that we're operating under here. So from a high level, the way these pipelines work is the following. As I said, the input to our system now is going to be a big set of images and their corresponding digit. And we have a lot of these, right? We of course have a lot more than just the 4 there, or you wouldn't learn a very good model. We have a lot of these things. And this is what we call the training data to our algorithm. This is the data we're going to build kind of our machine learning model based upon. And in particular, I'm going to generally refer to the input. So these things come in pairs. There's an input and an output, but that shouldn't be confused with the output of the algorithm. The algorithm outputs something else. This is all the input to the algorithm, the training set. But within this input, there is a real input, which I'm going to call X here, and there's an output, which I'm going to call Y. And so the goal of our machine learning process is to build a program which can map from these inputs to these outputs. Okay. And the way that works, and I'm going to go over how it works in a second, but we basically take all that data, a collection of data here, we feed it into a machine learning algorithm, and what comes out is what's called a hypothesis function. So this is the output now of a machine learning algorithm, not to be confused with the output of each data point. And the hypothesis function is a function that maps from inputs to outputs. So you can think of this like a program, right? It's a program that takes inputs that are images and outputs, in this case, digits. And it outputs some hypothesis function such that on this data, so importantly, on the data it was given, the output, when you take the inputs and feed it to that hypothesis function, it produces something close to the output. Okay? And that's the goal, in some sense, of machine learning. Now, we'll talk a lot more about how that's not the real goal in some sense, because the real goal is that you have some new data point, x prime, where you don't know the output, right? I have some new digit, I'm just going to write one, right? And I want my computer to recognize what that is. And so the real goal, of course, is to make a program which will work well on that new data point. We'll talk about this a lot more when we talk about the theory of machine learning. But today, we're actually going to largely focus on just the first part. How do you make an algorithm that will get close to your desired output for each input just on the pairs you feed it with? And then we'll talk later, next lecture, then even more in the theory lecture, about how this sort of implies its ability to generalize to new inputs it has not seen before. Okay, any questions so far? This is actually all there really is to supervised machine learning. This is sort of the paradigm. And of course, it can be much more complex when these outputs are more structured objects. But this is kind of the basic paradigm of what's called supervised learning. All right, so by way of now diving into this a little bit and talking about the math that we actually cover here, I'm going to start with a topic called linear regression, which many of you actually probably are familiar with already. You may have seen it in other classes, or if you've seen me give this presentation or a similar one before, you've seen it in this way. But this is actually kind of different how it's normally presented. I think linear regression is often presented as like trying to project data points onto a line and things like this. And I'm really going to phrase it in terms of a more general machine learning formulation. And so hopefully that'll kind of give you intuition about how a relatively simple algorithm can work in this kind of broad framework. And very quickly, we'll actually get to exactly these kind of problems where you can map high-dimensional objects like images to outputs. All right, so let me start off with a relatively simple prediction problem. This is one that's actually close to my heart. I do a lot of work in applications in power systems. And so I like this example a lot because it's a very sort of concrete example that actually has quite a bit of real relevance in the real world. So the question is what is the electricity consumption going to be in Pittsburgh tomorrow? Okay. Which is actually very important to know, because if you know how much Pittsburgh is going to consume tomorrow, you can never get it right exactly, right? Because presumably I could go, if I have free will, I could go turn on that light or not. So they couldn't get that, whether I'm going to do that. These operators don't know that about me. But it's surprisingly, people are surprisingly predictable, especially when a lot of these things are, driven by the same things people do every day, like turn on lights or turn on heaters and stuff. And so you can actually come up with a pretty reasonable estimate for this. And the better you can do, the better you can schedule your generators such that they don't produce too much power, right? Because the generators have to always be producing enough power to sort of supply everyone with whatever they want. That's kind of how we work. I don't phone up the operator when I'm going to turn on the light. I just turn it on, and there's sort of power waiting for me to use. And the more you can predict that, the less kind of excess power do the system operators in this region have to schedule. They can sort of be operating exactly at what I'm actually going to use. That's, of course, a simplified picture of it, but it's a reasonable intuition there. So the point here is that it's actually quite hard to build an a priori model of how much power people are going to use, right? You could think, okay, well, how much do people use? How often people turn on lights? What's the average wattage of lights people use in their homes? Things like this. Put this all into a big model and simulate it forward and see what people actually use, and chances are it will work very poorly because you'll make some little error in one of your modeling assumptions, which is going to create a huge error in your output. Let alone the fact that you can't account for people's presumably the fact that they have free will, and so they can change their minds a little bit. But what's relatively easy to do is to collect a big data set of past consumption, as well as some features that might affect consumption. So I'll sort of spare you the question here and let you know that by far the biggest indicator of the biggest factor that affects consumption is temperature. So especially in the summer months, consumption, at least in Pittsburgh, is driven largely by air conditioning. And so there's a very high correlation between temperature and how much power people use, which we'll see in 1 second. But what we're going to do is we're going to collect this big data set of all past days from some point in time till now, and say what their peak demand was. That's, in fact, we're only going to work with the highest consumption point that day, so we're only actually going to call it 1 point for each day, as well as the high temperature that day. Right? And you can extend this to hourly demand and going temperature as well as demand by hour, but let's just focus on the peak demand. So I'm going to take now the past 6 years of data. This is all real data from Pittsburgh. It's from the utility or the operator that governs Pittsburgh. And I'm going to plot, and then I also downloaded some weather data from, I forget which site it was, some weather site for the past 6 years. And I'm going to plot on this next plot the high temperature versus the peak power demand that was used in Pittsburgh. And as you can see, there's sort of this I should say this is only for the summer months, so June through August, when air conditioning is in fact the biggest driver of consumption. And as you can see, there's a sort of a very nice looking correlation here, right? As the temperature goes higher and higher, people use more and more power. And so now the question is, if I want to know how much demand there's going to be tomorrow, and say it actually is the summer right now. I know it's not the summer, so this wouldn't actually apply here. But say it's going to be a very bad model for tomorrow, actually. But say it is the summer. Say it's June 25th, and I want to know what are people going to consume tomorrow. I can just sort of how would I do that actually, right? How would I predict what people are going to do tomorrow? Well, sort of a very natural thing to do in this setting is something like forming a linear hypothesis. Okay, this is equivalent to really drawing a line through the data. Right, which is something you sort of naturally see in this picture. You sort of say, well, there's kind of this line that follows. Let's just pick kind of that line, whatever that line may be, and call that kind of our model. And the way we think about this formally is we think about the peak demand is approximately equal to some coefficient theta 1 times the high temperature plus some coefficient theta 2, where the first one is like the slope of the line, and the second one is the intercept of that line, right? Because you don't want to say when you have zero temperature, you need to have zero demand. So you want to be able to move the slope of that line as well as the intercept here. And the idea is that this kind of line acts as a model, right? Because given a new high temperature, I can just plug that high temperature into my model and say this is how much we're going to consume tomorrow. Ignore for the moment the fact that the high temperature is also a prediction, right? That it's actually a pretty good one. Weather forecasts the next day are pretty good, and they're very definitely being used by demand forecasting. So we'll predict what the high temperature is going to be tomorrow, but we'll just call that a set value. Then we'll plug that into our model, and that will give us a prediction for how much demand there's going to be tomorrow. And again, what this kind of looks like intuitively is sort of like drawing a line through the data. And then I look at my high temperature tomorrow on the x-axis here. I say, oh, it's going to be 80 degrees tomorrow. Again, not actually tomorrow, but some future tomorrow in July. And then I see where my line lies there, and I say, okay, we're going to have probably something like 2.15 gigawatts of consumption at its peak. So I'm going to schedule my big generators to generate that much electricity. So hopefully people have all seen something like this before. If not, this is self-contained, so hopefully this makes sense. But what I want to do now is formalize this in a little bit more detail, a little more mathematical notation, because this notation, this is a very simple problem, right? This is just sort of fitting a line to data. This exact same notation is going to carry over to much more complex machine learning tasks, including things like deep learning, which we're going to talk about shortly. So here's the notation I'm going to use. I'm going to refer to my inputs. Again, this is the input outputs in terms of those pairs of data points. So the input in this case will, in general, be a vector that I'm going to call xi. And I'm going to think of this as a vector in Rn. So n is the dimension of my input data. And actually, in the first case that we talked about here, for example, xi could be something like the high temperature of that day, of day I, plus actually just nothing else, just a constant term. And the constant term is how we're going to roll in that slope into this model nicely. So actually, you don't even really need this constant term, but adding it here will make our lives a little bit easier later. You could also add other things here, I should say. So you could also add something like, is it a weekend or not? Is it a holiday or not? These things also, as a matter of fact, do change people's consumption. But you could add whatever you want here, actually. The fact that it's one-dimensional in our case is I'm only doing that so that we can visualize it a little bit more easily. This could be as many sort of input features as you want. And the dimension of this input vector is always going to be considered a vector in Rn. So for our digits, for instance, the input vector would be like a vector in 28 times 28, which is 784 dimensions, right? Okay, so that's the first sort of ingredient of our algorithm. The second ingredient is the output. And then we're going to denote that by yi. I didn't say this part. I here varies from 1 to m. So I'm going to assume that I have m instances in my training set. Each one is an n-dimensional vector. People flip those terms a lot, so sometimes people will call this d and this one n. I'm going to use n and m, but that's just sort of notational. It doesn't really matter what you use there. So I have my outputs, and my outputs in this case are real valued. So the fact that there are real valued outputs is actually what makes this a regression task versus something like a classification task. So we'll see classification in a second, and that relates to outputs that are discrete valued instead of being real valued. And these things together, so both these things together, constitute what I'm calling the training set. And for example, in our setting here, we're running out of space, but yi was the peak demand. Again, for the ith day. Where did the eraser go? Okay, the third ingredient we have here are something called model parameters. So we have some parameters. And in general, for this entire sort of unit, I'll refer to the parameters as a vector theta. Sometimes that will actually contain a lot more things than just a single vector, and it's hard to kind of bundle all together, but I'm always going to take all our parameters and bundle them together. And for here, in the case of linear regression, and only linear regression, this actually ends up being a vector which is the same size as the input. So that's the fact that this is the same as the input size is important here, but this is an effect of linear regression. In general, you can have different numbers of model parameters as you have dimensions of your input. Okay. And these are the things that are going to define our last bit, which is our hypothesis function. Right? And so the hypothesis function is going to be parameterized by these parameters theta. And in fact, that is our fourth ingredient, is the hypothesis function. Hypothesis function. This is a function which I'll denote as h theta. So I'm doing that notation here to emphasize the fact that it depends on theta. So it really is a function in some sense of theta. But I'm going to think of this function as mapping between inputs and outputs. So in this case, it maps inputs in Rn to here, outputs in R. Though, again, taken more literally, this is actually a function of both the input and the parameters because it's defined by the parameters. Now, let me give a sort of a simple example to hopefully make it a little bit more clear. A simple hypothesis function, which is in fact what we're going to focus on entirely today, is called a linear hypothesis function. And that is h theta of x is just going to be equal to the inner product of theta and x. So theta transpose x, where we think these both as being vectors, that's going to be their inner product. But again, this is just equal to the sum from I equals 1. So I think I actually use j when I can here, of from j equals 1 to n of theta j times xj. In general, I might fault on this sometimes, but I will try to use I in my superscripts to index over different examples, and where I need it, I will use j to index into specific entries of an example. Yeah?
Do you mean n over there, or n because x from 1 to n, right?
So here, I definitely mean n. That's actually really important. X are vectors in Rn. So the hypothesis function takes a single input, a vector in Rn, and produces a real valued number. Okay? And the way it does that is by taking an inner product with my feature vectors, my parameters, and my feature vectors, and x, and that gives us a real valued output. So this is a single x here, and we are taking the inner product of x and the parameters. And I could write, xi here for any I. This is equal to that, but I'm just omitting the superscript I because we don't need it there. When there's no superscript on x, it means it's kind of a generic example. It can apply to any of them, and then we just omit it because it's just kind of cumbersome. Okay, so those numbers are going to be key to remember kind of throughout this whole lecture. So I will leave this up here and do kind of glance back at it if you can't remember what one of these things are. So superscripts always index over multiple points in my training set, multiple examples in my training set. Those range from 1 to m, and I use I to index over them. Each entry itself in x, or each entry x, each vector x has n dimensions, and I'll use subscripts and the letter j to index over those. And I will try hard to be consistent with that, but please, if anything is confusing, do interrupt me. Okay, so now the other question is, remember what I said was that the goal of machine learning is to find some hypothesis function that for our training data approximately would produce the desired output for all the inputs. Right? In other words, for all examples in our training set, we want yi to be approximately equal to h theta of xi. Right? Where approximate here, of course, is the key point here. How do I measure how good my approximation is? Okay. So I would like we want h theta of xi to be approximately equal to yi for all I from 1 to m. But how do I measure this kind of approximate function here? I'm going to do that through what's called a loss function. So the fifth ingredient, I guess, is what's called a loss function. And this is, in the case of regression at least, a function that takes as input two real numbers, r cross r, and outputs a positive number. Where you should think of this as measuring the difference between a prediction as generated by my hypothesis function and the true output. So the first one of these two is going to be the output of my hypothesis function, and the second one is going to be the actual underlying y. Right? So in particular, L, and it produces a positive number. There's no point ever making them negative. If they're negative and unbounded, it doesn't really make sense because you have like sort of losses which you try to minimize, and it doesn't make sense to have negative infinite loss. If it's negative and bounded, you could just shift it up by a lot. So you might as well just assume that they're always 0. Makes a lot more sense. I kind of want to maintain this break here. And so basically, L of h theta of x and y is a measure of how different my hypothesis function is, my output of my hypothesis function is from the true output. And so again, sort of a common example here is, in regression, is the squared loss. So a loss function we could use is that the loss between h theta of x and y is just, well, that's just take the difference and square it. That thing is small when they're close by and big when they're far apart. Yeah?
I'm a little confused by the notation here.
Okay.
Would it be okay to interpret this as really being a function of x and y, where h is a parameter? So it'd be like L of x and y equals h sub theta of x squared.
Let's see. So I think the question was, can you interpret this as being a function of x and y? I think it's better to think of it in terms of two y's. So think of it in terms of a predicted value for y and an actual value for y. So in some sense, the hypothesis output, right, is something that should be kind of close to y. It's real valued too. Again, importantly, it's real valued, right? It's in the same space as y. It's trying to get close to y, and so you should think of it as a function of a prediction and a real number, and the different, some measure of the difference there is this loss. And again, maybe it's even easier to think of it as squared loss as being a canonical example here, where we take our prediction of what the output is, subtract what the actual output really is, and then square the difference. Because that's sort of natural, right? If they're exactly the same, we're going to have 0 loss. If they're different, they're very different, we'll have very big loss. And so that sounds like kind of a natural way to measure difference between two real valued numbers.
So I guess the correct specification of the function's type would be replacing the first r with the image of h sub theta or something.
Yeah, sure. If h sub theta returns a different thing that's not r, then yes. This is actually always going to be r in almost all our examples until we get to multi-class classification. But for the most part, for this lecture, you can think of it as being always r. Yeah. Yeah. It takes the output of h cross the output. I mean, really, it should be the output of h cross whatever space y is in, and then it produces a positive real number. And this finally brings us to the canonical machine learning algorithm. And I really like this formulation because it kind of actually brings together, it turns out that virtually every machine learning algorithm you could ever come up with, and that people ever have come up with, though there are thousands of them, right? And you read about new ones every day, people are coming up with, and you say, well, what's it different? What's different about this? What's it actually doing? Well, they're all solving, to a first approximation at least, this problem. They are minimizing, again, this is an optimization problem now, so we're minimizing over theta. So we're finding some parameters that minimize the sum of losses on our data set. Minimize the sum from I equals 1 to m, of L between H theta applied to xi and yi. There are a few additions people often will put on that, but that's actually, to a first approximation, a very good description of what all machine learning is doing. Finding a hypothesis that minimizes the sum of losses on our training set. Where again, loss is some measure that measures how different we are from our prediction and the true output. So maybe I'll circle this as something to come back to. And as I said, virtually all machine learning algorithms have this form. So to specify, again, and you hear things like support vector machines or gradient boosting, and you hear all these really fancy sounding names. We're really good at coming up with clever names, I think, as a field. We do a really good job with that. Deep learning, it sounds so ominous yet powerful, right? What a machine learning algorithm really is just three things. It is, first of all, a specification of a hypothesis function. Secondly, specification of a loss function. How do I measure how good my hypothesis function is? And third, it's a way of optimizing this problem. And really every algorithm, even though they seem very, very different, are just different ways of solving that same, there's really three different ways of kind of combining those ingredients together. Okay. Any questions? Again, this is all supervised learning. I should clarify. This is supervised learning. Though it turns out actually unsupervised learning is not that different in a lot of ways. Surprisingly similar to this actually. But I'm not making that claim currently. Yeah.
How do you try to convince to other people that your model is good?
How do you convince other people your model is good? So if you have a machine learning algorithm that you want to convince everyone is good, there's a standard suite of problems you can run it on. And if it does better than existing algorithms on these problems, it's probably good. Now, there are also a suite of loss functions people have kind of decided are good measures, like just the number of mistakes it makes, right? That's a reasonable characterization of how good an algorithm is. So I think you have to do well on a problem better than other algorithms on a problem other algorithms have already tried to solve. It's a short story. Okay, so let's now formulate, and in fact I already have it over there because I was writing it down as I was going, except the last bit. Let's formulate our what's called least squares problem. That was my, I don't think I actually used that term before, but I'll use the term now. This is this problem of fitting a line to this graph, this data under certain loss functions. And in fact, what least squares really is, in some sense, is just the following combinations, or at least linear least squares is the following combination of things. The first thing is we're going to use a linear hypothesis function. That's what I wrote here. So certainly we could use more complex ones, and we will use more complex ones very shortly, especially when we come to deep learning. But here we're going to use a very simple linear loss function, where our hypothesis function, where our hypothesis is just some our parameters times the feature, the input features we have. Or again, those could be a lot of things potentially. That could be a high dimensional vector here, but our final hypothesis is going to be a linear function of those things. The second thing we're going to do is we're going to use, so that's point one. That's problem number one, or specification number one. Number two is we're going to use the squared loss function. So we're actually going to use this one here. Our loss is going to be the squared difference between our hypothesis output and the true output. Now you could ask, why do we use that one? Why not like absolute loss? That seems reasonable too, and I'll talk about that in a second. Actually, that other one. The reason why people use least, so people can justify, you can justify in all kinds of ways why you want to use least squares. You can say, oh well, it's, and we'll talk about this a little bit in probabilistic modeling. But you can say, oh, it's the log likelihood of a Gaussian model, and so, or I'm going to have these reasons for doing it. But really, the reason why people actually do it is because it's easy to solve. It's one of the few loss functions where we can actually come up with an analytical solution to this problem, and so it's nice for that reason. And so what this leads to is the machine learning problem, where I'm just going to take all my assumptions here and plug them in to that. So my optimization problem that I end up with is to minimize over theta the sum from I equals 1 to m of, well, h there is just an inner product, so it's going to be theta transpose xi. And my loss function is square difference here, so it's going to be minus yi squared. And that's my least squares problem. So now the third point of our ingredient list was how do I actually solve that problem? I need to formulate a way to actually solve this optimization problem. But fortunately, we've already covered optimization, so you probably already have a pretty good sense of how we go about doing this. And you could do things like, well, gradient descent, right? That seems to be a pretty reasonable way of attacking this. So we're actually going to write some gradients now. I realize gradient descent was probably a little bit hypothetical beforehand because there were no actual concrete gradients. But I'm going to write some now. And I'll write them in kind of compact form, though I'll try to describe why they are the way they are. Here's one method for solving the optimization problem. This is gradient descent. The idea is we're going to just have, and I'm going to write it into theta now, because theta are the parameters we're minimizing. I'm going to take theta, and I'm going to set it equal to, I'm going to repeat the following. I'm going to say equal to theta minus some step size alpha times the gradient of my objective, where my objective here is that whole sum, evaluated at theta. All right, so what is that gradient for this guy here? So I won't actually go through this in too much detail. It's not very hard to prove, but I'll sort of prove it only by analog to univariate calculus, because it really follows in the exact same way. So if I want to find out what my gradient of my objective is, which is in this case the sum from I equals 1 to m of h theta xi minus, oops, I should write the actual form there. Where's my, there it is. You will do a lot of manipulation with gradients throughout this course, so you'll get a little bit more familiar with these things. I'm going to be pretty brief here. Well, we can actually move the gradient. Remember, okay, so actually, just to remind everyone, the gradient is just a vector of all partial derivatives. The gradient is of a vector value, vector input scalar valued function. This is going to be the partial derivative with respect to each element of this. It's partial f partial theta 1, partial f, partial theta n. And so because of that, it obeys all the same rules, essentially, as univariate derivatives. So, for example, you can move it inside a sum. So this is equal to the sum of the gradients. Sum from I equals 1 to m of the gradient, the theta, of x transpose, or theta transpose xi minus yi squared. Now actually the chain rule applies too. So if we want to take the derivative of this whole thing, we will take the 2 out times this thing without the square there, and then times the gradient of that thing that's inside. So this equals to the sum from I equals 1 to m of 2 theta transpose xi minus yi times the gradient with respect to theta of theta transpose xi. Okay, and this one is actually very nice. It's very easy to come up with because this term here, remember, is just going to be equal to the sum over all j from j equals 1 to n of theta j xi j. And so if you just now look at this function and these derivatives here, what you'll find is that the only term that affects theta j is the corresponding xj. And in fact, it's just that one in a vector. In other words, the gradient of this thing, this whole thing, is just equal to xi. Okay? So in the end, the form is, I'm gonna just, for the sake of it, I think to match the slides here, I'll put the xi in front. This thing here is a scalar value, so I can of course put it on either side. So this equals, as a whole, the sum from I equals 1 to m of 2 xi theta transpose xi minus yi. And so to run gradient descent, we just compute this thing and repeatedly subtract it off our current parameters. And we know that will eventually push us to an optimum of our objective. I guess I didn't say it here, but another nice thing about this is this function is convex. It's a linear function squared. We'll also see it in a slightly different form later on, which involves a 2 norm, but it's a convex function in theta. And so if we follow this procedure, we will actually find the global minimum of this objective function. Yeah, Jonathan.
I forgot what the alpha was for.
Oh, the alpha is a step size. It's called a step size. It's sort of saying that if you take a small enough step, you'll decrease your objective, and you know you're going to. And so I'm kind of slipping that all on the rug right now. In practice, you guess what that should be, and if it's too big and you're oscillating around, you lower it. If you're going too slow, you raise it. So in theory, there's very nice theory about what it should be for different cases of functions, and that almost never means anything in practice, and so you just end up guessing. But yeah, it's kind of a small number. Pick 1e negative 2 or 1e negative 3, say. All right, so one more thing before I move on too much is that sometimes writing things out like this get a little bit annoying, and as you probably guess, you've seen my other slides, you know I really like linear algebra, and so it's really convenient to write this in linear algebra notation. And so in particular, I'm going to write the big matrix X as a matrix that contains all the different examples on its rows of this matrix. So this is going to be equal. It's a matrix which is going to be m by n dimensional, because there are going to be m rows, and each row is going to be an example. So there's n columns, and it's going to be equal to, x1 transpose, because x1 we think of as a column vector, so we're going to transpose and make it a row vector. x2 all the way to xm. And I'm going to do the same for y also. So that's just going to be a vector now. So I'll just call it little y. A little y without a superscript, which is going to be a vector in Rm. And that will be y1 all the way to ym. The nice thing here is once you do this, you can rewrite our entire objective very compactly. So this whole thing, this thing here, I won't write it again, but I'll call that my objective. Maybe I'll just call this actually, I'll just call this whole thing here f of theta. So if you write it in this notation, then f of theta, which is my sort of objective function, it's just going to be equal to the L2 norm squared of x times theta minus y. Remember, the L2 norm squared is just the sum of the squared entries. And the reason why this works is that in this notation here, the first entry, this whole thing here is a vector in Rm. And the first entry is going to be, the first the first row of y times theta minus the first entry in y, which is exactly kind of what we had here. And it's going to be the first thing, and then we're going to take, in the L2 norm, we're going to take that and square it. So that's going to be a compact way of writing our objective here. And also, if you do this kind of stuff, you pretty quickly learn some nice rules in matrix calculus. For example, the gradient of this thing, you can also write very compactly as just 2 x transpose x theta minus y. So this actually will check out. This is just the matrix form of this thing here. And you'll find that actually, and this also should look a lot like the scalar case, right? Because this is like a squared term. You pull out the coefficient, you have 2, you pull out the coefficient on the thing you're differentiating with respect to. And you had the term then without the squares. And so that's actually exactly the same as you do there. You have to just be a little more careful with managing the transposes and stuff like that. But that's sort of the easy rule there. Okay, I'm actually going to rewrite that in a second, but I'll save this for a minute. Because I want to, before I move on past least squares, I want to highlight one more thing, which is why least squares is so, what's this? Huh, okay. Why least squares is so popular, or one of the reasons why it's so popular. This is going to be a different way of solving our equations. So what I sort of said when I talked about optimization was that the goal of gradient descent is to find a point that, take a little step, that what we know is going to point to someplace a little bit lower than where we currently are, right? But actually also what's going on here is that we're trying to find a point at which the gradient is 0, right? So if I'm minimizing a function, and I know that my function is convex, meaning it always curves upward, then a condition for this being a minimizing point is that this, at least for a differentiable function here, is that the actual slope at the point that I find is going to be 0. So another way of thinking about this, and actually, of course, gradient descent, if it's at a 0 point, won't change at all. And in fact, you can prove that it will reach a 0 point no matter what, because that just is an optimum. So what we also kind of want in our conditions here is we want to find some point, theta star, where the gradient of our function evaluated at theta star is 0. And here 0 means a vector of zeros, right? This means the vector of zeros in Rn. So the nice thing about least squares is that our gradient is of a form where we can actually find a closed form solution to this gradient 0 equation. So remember, our gradient here, well, I just hit it, but the gradient of respect to theta of our function here, for the least squares objective, was 2x transpose x theta minus y. Right? This is again this whole thing here is a vector in Rn. You can check that. This is a matrix which is going to be n by m because we're transposing x. This is going to be a vector in Rm, so that outputs a vector in Rn. And in order to make this 0, well, we can just solve that as a linear equation, set of linear equations. Right? So what we do is we just move this thing here is going to be equivalent to setting. I'll just get rid of the 2 because I can just divide it by 2. It's going to be equivalent to setting x transpose x theta is going to be equal to x transpose y. So I should actually write this in terms of theta star here. This is saying this is equal to 0 at the optimum theta. And so x transpose x theta star equals x transpose y. In other words, theta star just equals x transpose x inverse x transpose y. And that is our solution to least squares. In fact, these are so common that it actually has its own name for these equations. They're called the normal equations. I think Gauss was doing these a long, long time ago. So these are not really new. They predate the word machine learning by 2 centuries. But yet, I think in some ways they are actually a canonical example of a machine learning algorithm. How you can find parameters that minimize some sum of loss functions on your data. Any questions here? Now this was a little bit fast if you haven't seen it before, but hopefully people have seen some elements of this before, and so this is, the new stuff here isn't too much. No questions? It's never a good thing when there are no questions. It means something's either it's too easy or too hard. And when you do this, in fact, the line that I showed before was in fact the least squares fit to this. I forget what my exact values here were, but when I solve this equation with x's, each x including the high temperature and then the constant value 1, and the y's being a vector of, and then of course, each row of the matrix, big X is high temperature and 1 for all the days. And then the vector y is a vector of all the peak demands for all those days. I get two numbers, theta 1 and theta 2, that when I plot them on the graph, they look like this. And that is the least squares fit through my data, the line that minimizes the sum of squared errors to all the points. Okay, so that's a quick question now. I had a hard time actually formulating this question when I was writing it, so hopefully I'll try to describe what I mean by this right now. So suppose I'm going to run least squares. I'm going to implement it in Python. So I'm going to implement it in Python just by using, say, numpy.linalg.inverse to form this inverse here, and then dots to form the matrix products here. And I run it on a situation where so that's what I did here, right? And in this case, I have two features because I have the high temperature and a constant term, and I have a lot of examples, right? I have M is very big here because I have many days. And so what happens in the opposite case? What happens actually if I run the same algorithm, but in a situation where I have higher dimensional features? So maybe I have a lot of descriptions of many days. I have it's the weekend, it's a holiday. I can't think of any other stuff. But what day of the week is it? How many hours of daylight were there? These are things that actually do affect peak demand. I could also add things that don't affect peak demand, like what my favorite color is on this day, if that changes day to day, I guess. But I had a lot of features, and I only have a few data points, or only a few examples. So N is very big here, because I have a lot of features, and M, which is the number of examples, is relatively small. So I only have like 5 days worth of data in the past. And I run this data, put it into my solver that I've coded up in Python. And so the question is, what's going to happen? And there are actually sort of two different axes that I'm asking about here, which I'm combining kind of awkwardly. The first is what happens to Python. So the first is Python. I wrote two Y's there. Python. It could fail, or it could not fail, succeed. That's the word, right? And then mostly that's we have this kind of the solution at the same time. There's also the solution. So that is, what is the actual optimal value? In other words, what's the value not of the parameters, but of the actual objective function I get when I minimize things. So this solution could either be 0, it could be finite, but non-zero, or I should say strictly positive. Less than infinity, or it could be infinite. And I kind of want to ask you, which quadrant do we lie in this case? So will Python succeed or fail? And I guess the first question says Python will fail because the true minimum is infinity. Python will will fail even though the true minimum is 0. So there is a minimum there, but it will not find it. Python will succeed and have strictly positive cost, or Python will succeed and have 0 cost. So I guess I didn't have a few of those options there, but hopefully the overall thing makes sense here. Let me open up the poll. My internet is being quite poor here. Let me see if it works on my phone. No, you can't open polls on your phone. Yeah, I'm actually not getting... Are there people on the network right now? Can people access it? Okay. Ariel, are you on? You can't access it right now? Just if you can open up the poll. Because you can't open it from your phone app, sadly. I can only mark it as inappropriate on Piazza on the mobile app. So I'm probably not uploading the video properly either if I'm not on the network. Oh, I'll go on, that's what I'll do. I'll go on my phone's internet. It's working? Oh, it's okay. So Ariel got it. Okay, it's open. We can. I'll try to reconnect while I'm doing this. Okay, there. This is a plug-in, maybe. Yeah.
Least square solver, that last line.
Yeah, it's just, you just implement this the simplest way you possibly could. Using, I think it says, using the normal equations in Python. So I'm implementing a solver that uses just this. Where this uses, say np.linealg.solve or np.linealg.inverse or something, .inv, right? One of those. Just doing it the way you would think to if you just saw that equation there. What was that? Oh, is this histogram showing? Oh well. I'll edit the next one so it isn't doing that. Don't look.
Doesn't always do that.
No, it's not supposed to.
It's doing that weird thing again where there's only one choice on mine that I
Is it the right choice? That's very bizarre. Huh. Yeah, I guess I checked the wrong thing when I. Okay, so we'll do 30 more seconds. You apparently can see what other people are voting, so it should be really easy just to pick the the. Okay, so someone. Wait. Now poll results. Oh, someone hid them. I couldn't see how to do that, so. Someone with more skill than I. All right, we're done now. Okay, so let me just move over and see what people. Wait, they should be visible now that they're not hidden. Why can't I? Can I make? There we go. Okay. I don't know. All right, so there's a nice, at least, plurality around the correct answer. So the correct answer is that Python will return an error, but the actual true solution is still 0. So let me try to convince you of that. So the true solution to this, to the objective, that is not the thetas, but the actual function value you get when you find the optimal solution, or I should really say an optimal solution, because there are often many of these things. There will be many of them, is 0. And the reason why is that we are trying to solve this matrix equation here. We're trying to minimize theta minus y. But in this case, there are actually more entries in theta than there are rows in the matrix y. In other words, you have what's called an overdetermined set of equations. And so just like actually in your simplex solver, what you can do is just pick at random some m columns of those, and I'm also going to assume here that there's some independent. That there isn't the rows are linearly independent here, though. Otherwise, you have weird situations. But I'm just going to pick m columns from my matrix here, and then I have a square system. I can solve that exactly and actually get a solution that has 0 cost here. In other words, I can easily find a theta such that x times theta equals y. And I can do that because here, this is n-dimensional. I have n free parameters. I'm trying to satisfy m equations. This whole thing is m-dimensional. So I have m variables. I'm trying to satisfy n equations. Sorry, m equations. And I can therefore always do that. Again, assuming that they aren't linearly dependent in some degenerate way. I guess if you answer that because you thought they were being degenerate, then that's right too. But I'm assuming they're not degenerate in some way. You can always find an exact solution, which will in fact make your error 0. Python, though, unfortunately, will not find that solution. It will just throw an error. And the reason it throws an error is that this matrix here is going to be what's called a low rank matrix. So it does not have full rank because this matrix here is the product of and this one here is going to be n by m, and this one here is going to be m by n. And if n is bigger than m, this is actually just exactly the definition of a low rank matrix. It's a matrix that does not have full rank in its breakdown. And so you try to invert that and it will throw an error. We didn't really talk about low rank conditions for matrices, so if you didn't know about that, don't worry about it. It's more just sort of a fact, interesting factoid to know, is that actually you will get an error if you try to solve that using Python or NumPy, the naive NumPy call, even though there actually is a solution that attains 0 error. So I think probably most people had, or a lot of people had some intuition about that. I think this one was almost right if you use a smarter solver in Python. So if you use like the pseudo inverse call instead of the inverse call, you actually will get a solution that gives you the correct solution. And so you were just maybe smarter in your implementation of your least squares function. But really not that smart because it'd be a lot slower in most cases. So you're only sometimes smarter. Yeah.
Just want to make sure I understood what you just said. So the thing you wrote up there is well defined, right?
The inverse is?
Yeah.
So the inverse is not. So when you have a matrix, right? That like if I have a matrix that, so say I take a vector x and then multiply it by x transpose, right? This is an outer product matrix. It has what's called rank 1 in this case. The point is a matrix inverse is something such that A times its inverse equals the identity. And I'll claim that there's no matrix you can multiply by that actually equals the identity. And so this thing here is just sort of a tempered version of that, where now I have a few more than just one. But it's still not sufficient to actually guarantee there's going to, or to guarantee there's not going to be an inverse. So you actually can't form any other matrix such that when you multiply it by this thing, you get the identity matrix. And so in order to prevent that, you actually need this thing to be full rank, and that requires that m is actually bigger than n.
Okay, so the thrust of that is that this solution is not really well defined at all unless m is.
Well, the solution in some sense, the solution to theta is not well defined, that's correct. The optimal theta, there actually is no single optimal theta. There's a whole space of optimal thetas. But they all attain 0 cost. So we know, again, assuming that there are certain rank conditions of this matrix here, of x, and those are ones that we think would be satisfied, actually, then there will be many solutions that all attain 0 objective value. It's just that there's no single one. So there's no notion of the solution to the problem. There's many solutions, and Python won't find it when you solve it. All right. Okay. So, actually going a bit slower than I intended. All right. So let me say one more thing before I move on to classification. I think we have one more poll here too. And that is, why did we pick the squared error? I mentioned this a little bit before too. And I guess, as I said, you can come up with all sorts of justifications after the fact about why you did this. But the reality is you probably did it, and we do it in general, because this is one of the few functions that actually does have a closed form solution. Despite that, I mean, and so in other words, you can write out something like this, which you typically cannot do for most loss functions, and so you have to resort to things like gradient descent, which are fine. They still work, but they're an iterative scheme instead of an exact single-shot solution, and so they're not quite as often seen as not being quite as nice if you can solve it exactly. And so I'm getting a weird. I can't actually see my screen. There we go. But we could use other loss functions too. So for example, the absolute loss function, where we don't take the square difference there, but we take the absolute value of the difference, is also a very reasonable measure of how different our prediction is from the actual solution, or from the actual output. And you can in fact play the same tricks with linear algebra as you did before. And in fact, this problem of minimizing the loss, where it's an absolute loss, can also be written in vector form as minimizing what's called an L1 norm of the difference between our predictions and our outputs, where the L1 norm of a vector is the sum of its absolute values. Right? So that's another optimization problem we can form that is, in some sense, by these three ingredients, or at least the first one of the three ingredients is the same. We have the same hypothesis function, but a different loss function. And so because of this loss function, we're going to have to use a different way of optimizing, or at least we can't use the exact solution way of optimizing the function. So we have to resort to things like gradient descent. It's actually, technically this function is non-differentiable at the 0 point because the absolute value is not differentiable at 0. And so this is actually something called subgradient descent. But you can compute the subgradient of this function. Actually, it looks a lot like this. It's just you have a sine term there instead of this thing. You have the sine of this thing. And other than that, though, you run gradient descent and the thing works pretty much as it did before to minimize this function. Okay, so one more poll question really quickly here. I went on my data here and I solved it for both absolute loss and the squared loss. Actually, I think I used the exact solution here. I didn't use gradient descent. By the way, you can solve this problem exactly, this one exactly, using a linear program. That might be a homework question or maybe an exam question. We'll think about that. So I did that. I solved it exactly. And one of the solutions, and I solved it with least squares, and one of the solutions is green and the other one is red. And so the question is, which is which? The third answer being, I don't have that good eyesight. Those look exactly the same to me, which is a perfectly reasonable answer here, actually, if you want to answer that. So I think I have access now. They'll let me edit the poll. Okay, turned it on already? Someone turned it on? Okay, turned it on. Okay, so it's open. All right, we'll do 30 more seconds because I realize I am kind of running a bit behind where I wanted to be today, but that's okay. I didn't intend to get through the whole next part, but I wanted to at least start. I want to at least start on it. So. All right, we'll do 5 more seconds. Okay, so close the poll. Whoever. Okay, there. No, I can close the poll too. But all right, and the results hit. Wow, I should do this more often. Just have someone else do all the work. All right, so here are the. Oh, again, a nice, nice distribution around the correct answer, but with some weight on the other ones. And C is a perfectly good answer as well. The lines could look identical. it's actually sort of an important point that they look very similar in a lot of cases. But indeed, the green one is the squared loss, and the red one's the absolute loss. And you actually can tell that from this figure. So the reason why you can tell it is that is by the nature of these loss functions. So and this also gets to why we might want to use one over the other. Though, as I should say, they aren't that different. So when things look pretty linear, yeah, it doesn't really matter that much which one you pick. But if you look at this function, the absolute function versus the squared loss function, right? The absolute loss function, for points that have, they're pretty far away from their hypothesis, you suffer a loss that's equal to how far away they are, right? So that's like bad, right? So you suffer bad loss. But with squared loss, you suffer bad squared loss, right? So that's even worse, right? So when there are really big errors, squared loss penalizes you a lot for them, whereas absolute loss just kind of says, okay. It's the same kind of thing with actually the medians we talked about versus the means we talked about in optimization. And so what I can kind of see here is that there's one point which is pretty far, right? That point right there is pretty far from that line, right? And what you'll notice is the green line is a little bit closer to that point, or would be a little bit closer to that point than the red line. So again, this is sort of hard to see, but it's actually this little thing there that gives it away what the answer is. So again, so that's why C was a perfectly good answer, especially for those in the back that might be. I see some people straining their eyes to look and see. In other words, the green one is pushing itself up a little bit more because it's suffering a very bad loss from that point right there, whereas the red one is not suffering as much loss there. And so it would rather fit the rest of them than kind of move the line a little bit to hit that one better. For this reason, actually, absolute loss is what's known as a robust loss function. It is not as affected by outliers in the data. So if there's one point that has a really big error, squared loss will actually try to fit that point a little bit, whereas L1 loss will just kind of say, I don't really care. And so it's called a robust loss function for that reason. And so there are differences that are important between these two things. But the other thing to note here is that when the data is relatively well behaved, there oftentimes is actually not that big a difference between these things. So whether or not it's important to use one loss function over the other will depend oftentimes on how good the model actually fits the data. Because if they're both, for example, could be made 0, then that's just the solution, right? They'll both find that same solution if they both can be made 0. So, the details here are really kind of only in certain cases where it matters which one you use over the other one. Okay, so in the little time I have left, I do want to get started with classification. So I might just sort of rush through this, and please come ask me at the end of the class if you have any questions about that. Because I want to introduce us to the next big topic in machine learning, which is that of classification. And so in classification, we're moving now from real valued predictions and regression to discrete valued predictions. This is what, if you've heard that term before, classification, it just means discrete valued predictions. There's two types usually that people think about. The first one is binary classification, where you have 0 or 1, or in our case actually -1 and +1 classes, so true, false answers. Is this email spam or not? Versus multi-class classification, where there are multiple different categories. So again, like the digits that we saw originally were of this multi-class variety. So to motivate this, I want to take an example that was very kind of famous in the literature. It was one of the big, well, not one of the big ones, but a large force kind of driving a lot of machine learning progress in the early 90s. And this is a domain of breast cancer classification. So the idea here is, and this is actually became a very, very standard data set, and also one with very large social and societal implications. And so the idea here is you want to determine, have a test to determine whether a tumor that you extract from a biopsy is malignant or benign. And this, oncologists and radiologists can do this very well. But this is something that, we do a lot of tests for people that might have cancer or not. If you tell someone they have cancer when they don't, that's sort of a bad thing. It's also bad in a very different way, but also equally or somehow more or worse bad if you tell someone they don't have cancer when they do. So you want to really know how, you want to really be able to accurately predict whether someone has cancer or not, whether their tumors they see are actually going to be cancerous or not. So what this data set actually consists of, and this is not, it's not a vision task. that from these things were extracted a lot of features people use. But what people did is that they took these biopsies. They take cells from a biopsy, and you stain the cells, and you look at them through a microscope. And then the researchers sort of would outline these cells, cells that are potentially cells from the biopsy that were either potentially tumorous or potentially malignant or benign. And this is what that looks like. So they take these little cells and they outline them in these white shapes. And then they create a bunch of features from these outlines. This is what they did. And this paper was from '92. So it was, again, sort of a very compelling application of machine learning that maybe now would all be done automatically, but back then, you had to do a lot of pre-processing in order to really get these things to apply. So they by hand kind of annotated these things. They used a little bit of computer vision to help with the annotation a little bit. But for the most part, they just annotated them by hand, circled each cell. And then for each cell, they computed or each cell that you highlighted, they computed a bunch of features like the area of the cell, the perimeter, the concavity, like how many, is it concave or not, or is it purely convex? Nothing to do with optimization, just the actual shape of these things. How many concave points does it have if it has some? And then they compute things like the min, the max, and the standard deviation for all these features over all the cells in the image. And those become the features of our data set. So here is a plot of two of these features in the data set. So this is a plot of the number of concave points on the mean number of concave points on the y-axis. So each cell may or may not have any concave points in it. A concave point would be something like this, where it kind of juts in a little bit like that. So the mean number of concave points it has, plus the mean area in pixels of the cell. So the average number of concave points for all of them. That's why it's less than. Most don't have any concave points. That's why this is less than 1, but a couple of them might. And then the mean area in pixels over all the different cells. And they can plot then the occurrence of benign and malignant tumors for these two features. Right? So the points marked in blue are benign tumors. So those correspond to slides where they created the features for a benign biopsy. And the red ones are malignant. So it seems like, at least, as both of these features increase, so as they are more concave regions, or as the cells become bigger, those are both indicators that this is more and more likely to be a malignant tumor. And just like linear regression, the picture you should have in your mind is one of drawing a line through the data. For linear classification, the picture you should have in your mind is one of drawing a line that separates the two classes. Right? So it's not like we're drawing a line through this class. That wouldn't be very meaningful there. Right? That would be kind of like predicting the number of concave points from the mean area, which actually could be interesting, but it's not what we're doing here. What we're trying to do here is we're trying to predict the label of the point, be it malignant or benign, based upon these two features. And a linear classifier will separate this feature space with a line. Now, the way we're going to do that is actually very, very similar to the linear regression case. And I'll mention this right now, though we'll start here again next time. But we can actually formulate everything in the exact same way as before. So we actually have everything the same. We have inputs that are in Rn. We have outputs, though, instead of being in Rn now, they're now in -1 and +1. Right, so we have binary labels on our points. We'll get to multi-class later, or at least on the homework we'll get to it, but if not in class and on the homework. We have model parameters, and we have a hypothesis function. And importantly, actually, our hypothesis function, though it might sound odd, is actually still going to map from vectors to real-valued numbers, where the number that it maps to can be interpreted like a level of confidence in our prediction. Right? So if the number is very positive, then we're sort of very sure that it's going to be a positive class. If it's very negative, we're sort of very sure it's a negative class. And if it's 0, we're kind of not sure either way. Right? So that's actually going to be the formalism. So it's important that our hypothesis actually still maps from Rn to R, even though we're predicting binary values here. And what I'll end on, this last slide here, is just sort of understanding what this picture means in terms of that formalism. So here what we actually had was we had that the x, our features here, were the mean area, the mean concave points, and 1. And so our feature is a function, our hypothesis function is a function of both those two inputs plus a constant term, and then maps to a real number. So the way to actually visualize this is you should think of this as the hypothesis is a plane, sort of a 3D plane in this space, right? So it kind of is some plane that's positive in the whole red region, passes through the z equals 0 plane at the black line, and is negative in the blue region. So it's important that we're not talking about predicting like this y-axis here as a function of the x-axis. We're talking about predicting kind of a third axis in pictures like this, which is going to be positive, where the output should be positive in the red region, or i.e. where the points are red, and negative where the points are blue. And that's going to be kind of the paradigm for classification. And of course, because it's a linear hypothesis function, that line where it hits 0 is going to be a line, right? Because we can't. It's a linear function, so where it passes through the z-axis is going to be a line, and that's kind of the paradigm for how you should think about these things. So next time we'll talk then about how you define a loss function now in this kind of odd space where you have binary and real value predictions, but it ends up being very, very similar to the previous case.